In our first example, we're going to look at a question that asks us to find and classify the stationary points of this function, x cubed minus 3x. Now, this question has two parts to it. The first part asks us to find the stationary points, and the second part asks us to classify them. And to classify, that just means to decide whether the stationary points are maximum points, so like this one, whether they're going to be minimum points, like this one, or whether they're going to be some kind of horizontal inflection point. So something like this, a place where the function kind of just comes up, flattens out, and then keeps going in the same direction. So to do each of these parts, we're going to need to apply our knowledge of derivatives. With any of these questions, the first thing I do is to find the first and the second derivatives straight off the bat. So if this is our function, then I'm going to have to find my first derivative using the power rule. That means I take the power here, bring it down the front, so this is going to be 3x squared. So I have to reduce that power by 1, minus 3x differentiated is just 3. My second derivative, bring the power down again, I get 3 times 2 is 6, x, and of course that minus 3 just goes to 0. Now, first part of the question asks us to find the stationary points, and we know that stationary points exist when the first derivative, I don't know why this isn't working today, there we go, the first derivative is equal to 0. So we're going to take our first derivative, which we said was 3x squared minus 3, and we're going to set it equal to 0. And to find out the answer to this, we need to solve for x. So to do that, I'm going to try and get the x on its own. To do that, I'm going to take minus 3 across the other side. To do that, I have to add it to the other side, so I'm going to get a positive 3. Then I need to divide by my coefficient, which is 3. 3 divided by 3 is going to be 1. And then finally, to get x on its own, I need to take the square root, but not just the square root, I actually need to take the positive and the negative square root, because there's two possible things that could square to give me 1. And those, of course, square root of 1 is 1, so the two options are 1 or negative 1. So this is basically all the information I need to be able to find the stationary points. This tells me that the x-coordinates of the stationary points are 1 and negative 1. Now, it's good to be able to find the x-coordinates of the stationary points, but if at some point I actually want to graph this thing, I'm actually going to need to find the y-coordinates that go with it. So just as an aside, I think people sometimes get confused by this. This is just an aside. I need to find the y-coordinates that go with these x-coordinates. So I need to find y-coordinates to go with these. And to do that, of course, we substitute those x-coordinates into the original function. So in other words, I'm going to find f of 1, that'll tell me the y-coordinate that goes with this x-coordinate, and I'm going to need to find f of negative 1. And of course, our original function you remember, was f of x equals to x cubed minus 3 x. So substituting 1 into that equation, I'm going to get 1 cubed minus 3 times 1. And substituting negative 1, I'm going to get negative 1 cubed minus 3 times negative 1. So 1 cubed is 1, minus 3. 1 minus 3 is minus 2. Working this one out, negative 1 cubed is negative 1. Negative 3 times negative 1 is positive 3. You're going to get positive 2. So that tells me that the y-coordinate that goes with 1 is negative 2. So the point 1, negative 2 is a stationary point. And the coordinate that goes with negative 1 is 2. So, negative 1, 2 is a stationary point. And so that is the first part of this problem. We've successfully found where the stationary points are. The next part is to classify them. To classify our stationary points, we're going to actually use the second derivative. And the reason the second derivative is going to be useful is because the second derivative, remember, told us about the concavity. And the concavity would be able to decide which of these three cases we have, whether we've got a maximum, whether we've got a minimum, or whether we've got some kind of inflection point. And the reason for that is if you think about a maximum point, okay, a maximum point is always somewhere where the graph is going to be concave down, because it's got to be the highest point. Everything around it must be going downwards. So if we've got a maximum, then it's concave down. And if it's concave down, that means that the second derivative is less than 0. That is, it's negative. So the second derivative less than 0 means concave down. Similarly, if we've got a minimum, then it's got to be concave up. And if it's concave up, the second derivative must be greater than 0. So it's going to be positive. If we've got the third case where we've got an inflection point, well, that's somewhere between concave up and concave down. So that means that in this situation, the second derivative is going to be equal to 0. Okay, it's not positive and it's not negative. So this is called an inflection point. And in this particular case, it would be called a horizontal inflection point, because a horizontal inflection point is an inflection point, a change of concavity, and a stationary point as well. So I should say that this is a horizontal inflection point. So what we're going to do is we're going to apply the idea of the second derivative to our two stationary points that we've found. I'll just give myself a little bit more room to work with here. Okay. So remember, our second derivative is equal to 6x. So our second derivative so remember, our second derivative is equal to 6x. And from the previous question, the two stationary points that we need to classify are this one here, 1, negative 2, and this one here, negative 1, 2. And we really only need to think about the x-coordinate if we're going to be classifying. So to classify these points, we're going to plug those x-coordinates into the second derivative. So to classify this first stationary point, we're going to need to work out f double dash. I'll try drawing that again. Doesn't want to work for me today. F double dash of 1. In other words, 6 times 1. That's equal to 6, but more importantly, the thing that we're interested in is the fact that that's greater than 0. So if the second derivative is greater than 0, well, that means the graph must be concave up. So this point is going to be a minimum. So we're going to put that down, that therefore, therefore, this point, 1, negative 2, is a minimum. Now we're going to classify our second stationary point. So we're going to think about our second derivative once more. Probably didn't need to write it out again, but I did anyway. And so for this stationary point, we're going to find f double dash of negative 1. So this will tell us about this stationary point. And this stationary point is, when I substitute it in, I'm going to get 6 times negative 1. 6 times negative 1 is negative 6. And more importantly, that's less than 0. So if we've got the second derivative less than 0, that tells us that we are concave down in this location, and therefore we're going to have a maximum. So therefore, this point, negative 1, 2, is a maximum. And so now we have found and we have classified these stationary points. Now that's all that the question asked us to do. But what I'm actually going to do is I'm actually going to graph these because I think it's good for us to have a good concept of what this actually means in terms of the geometry that we're dealing with here. So based on these things, we have found that this point, 1 minus 2, is a minimum, so I'm going to mark that point on. 1 minus 2 is a minimum. And negative 1, 2 is a maximum. So negative 1, 2, that point's going to be a maximum point. And we're dealing with a cubic here, so we kind of know the rough shape that that's going to have. We know that it's going to have something like this going on in this direction. And the right-hand side's going to come down like that. Go back up again. I'm not being too precise about the x-intercepts because we haven't found those yet. And so that should be the shape of the graph that we are drawing.